Hi there, guys. Welcome back to another episode of Chemistry Complete. And in this episode, we are going to be focusing on the organic chemistry concept of resonance. Now, resonance is something that's usually covered in general chemistry, but it really comes into play in organic chemistry when you start explaining the stability of compounds, and basically whenever a compound has an excess charge. Resonance is the ability to distribute that charge over multiple locations in order to increase stability. So one of the terms that we use quite often is delocalization. And we say that whenever a molecule has resonance, it has the ability to delocalize electrons. So we're going to delocalize electrons over multiple atoms in the molecule, or multiple sites. So what does this term mean, delocalize? Well, if you consider something local, a community, if you think about your local grocery store, it means it's within the area. It's in one specific location. So delocalize or delocalization means to spread out or to smear out over a large area. And that's exactly what we're going to do. We're going to take electrons or excess charge, and we're going to delocalize it or spread it out over the entire area of a molecule. So there are a couple rules that we're going to want to consider as we go along here. But before we get to those, we want to take a look at an actual example of resonance. So one of the simpler examples to utilize is, a lot of people know of acetic acid. So acetic acid is a carboxylic acid. It's the type of acid found in vinegar. And if we expose this to some sort of base, we can deprotonate the carboxylic acid portion and leave an O- in its place, right? So let's put in our lone pairs here. I should come back and include the lone pairs on our oxygens over here. And what resonance is going to do is it's going to take the negative charge that's left behind, and it's going to spread it out between the two oxygens that are present here. Now, in order for resonance to occur, you have to have lone pairs of electrons and or, usually a combination of both, pi electrons. And these need to be one space away from one another. So they should be adjacent to one another on the organic molecule. So we're going to keep these one space away in order for resonance to occur. So when we have resonance, think about a lone pair. If you have a lone pair of electrons, and a lot of times people call these non-bonding electrons, a lone pair is equal to 2 electrons, right? And then whenever we have a bond, and usually in organic chemistry we're talking about covalent bonds, we're dealing with 2 electrons, right? So if I have something like a hydrogen and a carbon, the bond right here contains 2 electrons being shared between them. So we're moving electrons back and forth. We've got 2 electrons anytime we deal with a lone pair, 2 electrons anytime we deal with a bond. And for resonance, we're going to be dealing with a lone pair of electrons and or usually a combination of both, pi electrons, pi being double bonds or triple bonds. So what happens? You've got a negative charge here because of the excess electron property. These electrons right here, it could be any of these 3 because all the pairs are equivalent. They can be donated in between the oxygen and carbon to form a double bond. Now if that happens, the carbon here would have 5 bonds, and carbon is not allowed to have 5 bonds. You cannot basically surpass the valence set of electrons that carbon could take on, which would be 8, the octet rule, because it only has s and p orbitals. So at the same time this happens, we need to move these electrons up onto the oxygen, right? And so when we have alternate resonance forms, we usually use this double-headed arrow, which represents the fact that we can go between both of these forms And in fact, both of these are valid forms of the molecule. Now I have an O- up here because that set of pi electrons has now been donated to the oxygen, and the other oxygen took a lone pair and created a set of pi electrons as a pi bond. So there we go. We can go back and forth between these two. So I'm going to clear this and show a little bit of a better representation. All right, I have this, which would be the deprotonated form of the acetic acid. And this can very readily switch by forming a double bond between the carbon and oxygen there. And this oxygen takes back a pair of electrons so that we don't have a carbon with 5 bonds. Remember, you should never have a carbon with 5 bonds in organic chemistry. We have an alternate form here. Okay, this is not an isomer. When we're dealing with isomers, we're breaking single bonds and creating new, we're basically rearranging the structure. This is the same structure. I could turn this around and I would get the same exact compound. So this is an example of resonance. So why is resonance important? Why would I want to spread a negative charge out between these two oxygens? And by the way, this could reverse. So I could just as easily go back down here and put this over here, right? So why is resonance important? Well, it's really important due to stability. And so the way I like to explain resonance is that if you imagine a charge, a formal charge, a positive or negative, we're dealing with a negative right now, is a situation that is high energy and low stability, right? So think of a charge as like a very hyper child. The child is screaming, it's out of control, it's got very high energy. And that creates a situation with low stability. So if that's the case, you want to basically find as many opportunities to get people to watch or balance the energy of this child as possible, right? So what we're saying here is each oxygen in this case that takes a turn with the negative charge is a responsible adult in that scenario that's trying to help calm the out of control child down. So by delocalizing the energy, we're going to delocalize the charge, the energy associated with that charge. That's going to lead to higher stability, and that's a good thing. Molecules are always going to be looking for higher stability and lower energy when possible. And that's exactly what resonance does. It spreads the charge out between the two. So one of the things that's important, because I said there were several rules, the first rule you want to realize is that individual resonance forms, so we're talking about the specific ones that we're drawing out, individual resonance forms do not exist. So what do I mean by this? Well, what I mean is that electrons, exist. Okay? Electrons are constantly in motion. And so if I'm dealing with the electrons that are being passed back and forth between these two oxygens, right? Basically, this dotted line represents the electrons going back and forth. So sometimes this oxygen is in a double bond state, sometimes this oxygen is in a double bond state, and there is a negative charge spread between the two oxygens. Okay, and so this is probably a more accurate representation of resonance. What we're really looking at is an average charge that's being spread out throughout this molecule right here. We have an average charge that's being sent between these two oxygens. And that's beneficial because what we're really saying is that each oxygen has about half a charge on it. It's not quite that simple, but it's better than one oxygen taking the full charge and the other one being neutral and not having to handle a charge at all. We're basically trying to help spread this charge out while we're working with this. Okay, so individual resonance forms do not exist. So why do we draw them? because it shows the location where we would find extra electrical activity. It's being spread between the two oxygens. So theoretically, it's an important exercise to understand where resonance forms come from, why they exist. However, that in reality, these resonance forms do not exist in isolation. It's really an average between the two. All right, the second rule that we want to consider is that when we're dealing with resonance forms, we can only move, and we talked about this a minute ago, we can only move pi electrons from bonds and lone pairs, or non-bonding pairs, whichever you'd like to call them. Okay? So the biggest key here is that you cannot, and you should not, break sigma bonds. So sigma bonds, we're talking about single bonds. Hey, if I were to take something and break it apart and reassemble it, I would be creating a structural isomer, not a resonance form. So for instance, if I were to take this right here, right, and somehow I attempted to rearrange it so that it looks like this, this would not be a resonance form, okay? This would be a structural isomer, and a very poor one at that. This is not a proper organic isomer, but you cannot take these and rearrange the bonds like this. So if you looked at the examples I had before, right, I'm dealing with the same structural arrangement. I'm just moving the double bonds and the lone pairs of electrons back and forth between the two areas. I have not structurally altered this in any way as far as an isomer would be concerned. So rule number 2, only move pi electrons in lone pairs. You should not be breaking single bonds anytime that you are going through this. All right, the third rule that we want to consider is the fact that not all resonance forms are equal contributors. So let's say are equal in delocalizing electrons, right? Okay, so what do I mean by this? What I mean is, let's take a look at an example here where I've got something along these lines. Right, so I've got a negative charge on this oxygen. It is adjacent, or one space away, from a set of pi electrons. So what I could do is I could take these, form a double bond, and then push a set of electrons onto the nitrogen. So the alternate resonance form that I would have here would be a double bonded oxygen. I would have a nitrogen that has a double bond now, and the nitrogen takes on an extra pair because of this bond that moved and deposited a set of electrons here. So now the nitrogen has a minus charge, and these would be the two resonance forms. So these are not equal in terms of their contribution for the delocalization. The oxygen has higher electronegativity. And if I have higher electronegativity, that means I have a higher affinity for electrons, and therefore that would make this the major contributor. This would be the major resonance form, or in other words, because we don't have individual forms, the negative excess electrons would spend more of their time around the oxygen than they would around the nitrogen. And that's because oxygen has a higher electronegativity than nitrogen does, right? This has a large partial negative. This would have a slightly smaller partial negative in comparison. And so if we're talking about hosting extra electron property, the group with the higher electronegativity is going to be the one that's better suited for that, whereas this is lower electronegativity. And so this would be considered, it's still a resonance structure, but this would be considered a minor contributor. So that doesn't mean that we always have major and minor contributors. It just means that not all resonance forms will be equal. So let me give you an example where they are equal. If I take carbonate, so carbonate is CO3 2 minus. If I take carbonate and I look at the Lewis structure, it's going to look like this. So I've got one neutral oxygen, and I've got two of them that would end up with negative charge. So when I take a look at this, I could take one oxygen and create a double bond and move the negative charge up to a different one. So my alternate resonance form here, I didn't touch anything on the left, so that oxygen is still the same, right? I now have a double bond oxygen on the right here, and then up top I have a new negative charge. So I'm passing the negative charge around here. These are equal contributors. There is no major or minor contributor here. They're all equal to one another. Okay, so no major contributor in this case. And that's because these are all oxygens that have the same positioning around a carbon. So another example would be something like nitrate, right? All of these oxygens right here, now the nitrogen would be positive, all of these oxygens are equal to one another relative to the nitrogen. And so you don't always have major and minor contributors, but it's possible. You shouldn't assume that every single resonance structure is equally delocalizing the electrons in comparison to another. And then finally, rule 4, which tends to be pretty straightforward, is that you must follow good Lewis structures, or you must observe good Lewis structures. So we'll say good/proper Lewis structures, right? So what does this mean? This means that I cannot turn around and say, oh, I have a resonance structure here, and this resonance structure has a carbon with 5 bonds. No, you cannot move around bonds so that carbon has 5 bonds, because now you're violating valence electron rules and VSEPR theory and Lewis structures. That's not permitted. So everything must follow and have proper Lewis structures whenever you're dealing with resonance. So one more time, the purpose of resonance is to take a high energy, high charge, formal charged situation and delocalize it over multiple areas so that we're basically spreading out that charge and helping to stabilize the molecule. And this is going to become very important later on in organic chemistry. So it's really essential that you get this skill down now so that you can explain and understand certain phenomena that will occur later on as you proceed through your organic chemistry course. So that's about it. I will try to post some sort of a practice for resonance in a little bit. But other than that, thank you for following me. Please remember to like the video if it was helpful. You can comment and I'll be happy to get back to any questions. And subscribing will be the quickest way that you can get any new videos that I release. So other than that, this is Professor Tomney for Chem Complete, and I will see you guys for the next lesson. Thanks a lot.